So we ended last time with Einstein's field equation, and let's take a look at it here. Okay, it said that the Einstein tensor, second rank symmetric tensor, was proportional to the energy momentum tensor. Okay, and this is a pre-field theory course, so we don't have a lot of examples of the energy momentum tensor, but we know how to take a single particle and make its energy momentum tensor. We've demonstrated that before. Okay, it's just the basically the mass of the particle times the outer product of its velocity. Okay, u sub nu. Okay, or in this case with alpha beta, it would just be proportional to the alpha component of the velocity times the beta component of that velocity, and we saw how that worked in the case of Newton's Poisson equation for the potential of gravity generated by a mass. Okay, so we're writing it this way, and I remind you that the Einstein tensor is made out of the Ricci tensor and the Ricci scalar in this combination, okay, in such a way that this combination has no divergence. Okay, when the covariant derivative hits it, it's contracted against either beta or alpha, you get 0. And we had to do that because we want the concept of energy momentum conservation to go through in a curved space-time. So on the right-hand side, we write down the energy momentum tensor. We want it to be conserved. So I apply the covariant derivative to this formula, and both sides vanish. Okay, and sometimes we'll write the Einstein equation this way, but other times we'll choose to write it explicitly in terms of R alpha beta. Sometimes for calculations it's a little bit more convenient to do that, and then we did a little bit of arithmetic, and we found that we could write it that way, picking up an additional term that was proportional to the trace of the energy momentum tensor. So just some arithmetic to carry that through, and so this will be the Einstein field equation, or equivalently this one as well. And you know, the promise of the equation is that it states that the energy momentum density in a certain region of space-time generates the curvature of that region of space-time. Okay, that was the intuition. That's the principle behind the equation, and we have to see if it works. We have to make friends with this equation, and that's the first thing we're going to start doing. We'll look at it in various situations. Strong field cases, we'll look at black holes. Weak field cases, we'll look at gravitational waves, and we want to see some of its properties. Well, first of all, let's compare it to something we're very familiar with, and that's Maxwell's equations. And Maxwell's equations written in 4-vector notation. Okay, I'm back to Minkowski space and just doing a special relativity in good old flat Minkowski space. Maxwell's equation writes that the divergence of the field strength tensor is proportional to the current. Okay, and this is hiding a conservation law, just like the Einstein field equation is doing. Because if I take the divergence of this equation, shown here, I'll get a second derivative applying to F mu nu. And then I remember, okay, that F mu nu is anti-symmetric. Within F mu nu you have the E field and the B field, and we learned how to distribute them among the elements of the anti-symmetric 4x4 tensor, F mu nu. So it's anti-symmetric in these two indices, but this object, of course, in flat space is symmetric. Doesn't matter which order you apply the partial gradients in flat space. And so you do the sum and you get 0 because it's anti-symmetric up here, it's symmetric down there. For every positive term you have a negative term, and sums to 0. And that's great because on the other side of the equation you have the 4 divergence of the current being equal to 0, and that's the statement of current conservation. Okay, and that's a basic principle of electrodynamics, the conservation of current. Charges don't just don't materialize out of anywhere. They move continuously, and the charge is conserved at any particular moment. If you have a charged 2 particle, it can decay into 2 other particles, but the total charge will be conserved, and it'll be conserved locally. Okay, this is a local conservation law. Okay, we found out that those are the kinds of equations that stand the test of time, in the sense that if they're true in one frame of reference, okay, and they're written in tensor notation, they're true in every frame of reference. We needed locality in the equation to give us a sensible conservation law. The idea of conservation laws that are non-local worked for Newton, but it doesn't work in a theory with a finite speed limit, as we studied a great deal in special relativity. Okay, so now we come back to general relativity, and we want to take a look at conservation laws there too. Well, the conservation law we're given from Einstein's field equation, or the generalization of this type of a conservation law to curved space-time, is that the covariant derivative hitting the second rank tensor gives me 0. Okay. So I remind you, in flat space-time, that gave us energy momentum conservation. We took t with one of the indices 0, the other indice ranging from 0 to 3, integrated it over all of space at a particular moment, and then we learned that this expression stated that this quantity was constant in time. Well, it's the same manipulation as going back here again and seeing that the integral over all of space of J0, the charge density, is constant in time. That's a consequence of this differential equation. And so look back at your notes for the details of doing the proof. But that's the idea of it, and we get a conservation law, and that's critical. Okay, so energy is conserved. Energy can flow into a region and flow out of the region, but it'll do so with in a conserved way. This equation is smarter than that. It also conserves a form momentum. Okay, the components of T0I are momentum-like. Okay, and that will be and those integrals will also be conserved. Okay, and it has other conservation laws as well in it, having to do with stress, and maybe we'll discuss those later when we take closer looks at energy momentum tensors. Okay, now this is an interesting conservation law because of course it brings in curved space-time. Okay, because the covariant derivative depends upon the curvature of space-time. And in the curvature, that's where your dynamical gravity field appears. Okay, so let's see how that works. Let's write out this equation for the simplest case that we have. Okay, which is basically just a particle having an energy momentum density in its rest frame of rho. Okay, times u nu. That's a candidate for an energy momentum tensor, as we've discussed, and we'll understand it better as we do more and more with it. The only thing we really know about it at this point is that the T00 component, okay, is basically just rho times c squared, okay, and that's just the source of gravity in Newton's world. Okay, and then we generalized it to to make a tensor out of it, so we can discuss it in the context of general relativity, right? We were thinking about starting with Newtonian physics, and then trying to write those equations, or at least some of the objects in those equations, in tensor notation, so that we can take them, okay, to curved space-time described by a Riemannian manifold. Okay, well let's take this equation and work on it. What does it say? Well, here's the divergence of T mu nu, and the divergence I can have it hit. Okay, the first two terms. This is density times velocity. It's like a mass current, and then it will distribute itself and hit the last term as well. Okay, well let's stuff almost looks familiar, but let's work on it a little bit. Let's contract this equation with the velocity sub nu. Okay, So why do I do that? Well, if I do that, then I get the velocity contracted with itself. Well, that's u squared. That's equal to c squared. Okay, for the 4-vector velocity. Okay, its length is c squared. Okay. How do I know that? Okay, well, I just jump into, I just take the particle, and I view it from the perspective of its inertial um, reference frame. Okay, so it's at rest in an inertial reference frame. Okay, a tangent space to the curve manifold at that particular position. Okay, what's its components then? It's at rest. So u mu is just the only non-zero component is the 0th one, and it's c. Okay, so u times u is just c squared. It's just the way we would do it in special relativity, but in this particular case, we choose a coordinate system which is flat, and I can always do that in a curved space-time because I can look at what's happening at a point, okay, and at the point I can always choose the Minkowski metric as we've already seen. Sometimes I refer to that as saying I jump into a freely falling frame. Okay, that's one way to say it. Another way to say it is to use the mathematics that we had last time and argue that I can always choose the Minkowski metric at a particular point. Okay, and I can choose the gradient of the metric to be 0 at that point. I can't get rid of the second derivatives, that's curvature, but that's all I need to make the point here that u squared is equal to c squared. Okay, so I get this equation, and here's okay, and so here I have another fact of u sub nu down here. There's not much I can do with that, okay, but but it does have a simple look about it. The claim is that the second term is 0 by a trivial observation. So let's check it. So it's u sub nu, d sub mu, and then u upper nu. So they're contracted across. Okay. So here, let's take a look at that. Well, let's start out with 0 and take the covariant derivative of a constant, c squared, and then write c squared as the inner product of u with itself. Okay, then I distribute my derivative across the two terms, and I look at them and I say, oh, they're identical. Okay, and they are of the form u sub nu, d sub mu applied to u upper nu. And that's exactly the second term I had. Okay, so that term, it goes away, and I learn a conservation law. Okay, I learned that in my curved space-time, that the divergence of the energy current is equal to 0, and that's good. Okay, I certainly want that. That's an ingredient in conservation of energy, certainly. Okay, so but now I have this. I can substitute it back into the original equation I had, which was the divergence of t mu nu was equal to 0. I had two terms there. Okay, and so and so I see that one of the terms is 0, so that the other term has to be 0, and there it is. Oh, well, let's look at that. What does that say? Okay, that says that the derivative of a tangent vector. Now let's think of the particle as moving along a curve. Okay, x sub mu. Okay, that sweeps out a curve, and the tangent vector to that curve is the velocity. So this says if I take the covariant derivative of the tangent and project it along the curve, I get 0. That's the equation for the geodesic. Okay, that's just the statement that the particle moves along a geodesic. Okay, and that's what I state here. Okay, in particular, I can go back to my equation for the geodesic, which was the covariant derivative of u with respect to tau is equal to 0. Okay, and then we wrote that out in a particular coordinate system. Okay, as the covariant derivative in the mu coordinate applied to u nu contracted against u mu is equal to 0. It's basically just a chain rule operation. I'm just taking the derivative with respect to tau, and I'm writing it by the chain rule as derivatives in my particular coordinate system. Okay, but that then just expresses. See, this thing is written in a general abstract way. You take the covariant derivative of the tangent vector along a curve. Okay, as no coordinate system there. I introduce a coordinate system so I can talk about the covariant derivative in the four different directions of my coordinate system, and then this is how it looks, and then I see this is how that is. Okay, but then of course I can work on I can work on this and write it then down. Okay, remember we had the explicit expression for the covariant derivative. It was naive direct derivative. Okay, corrected for the curvature of space-time with Christoffel symbols. So writing it down, it becomes this, and then writing u as dx by d tau, I get my familiar geodesic equation. And so I'm just harping on the fact that this is one way of writing down the geodesic. Okay, and I like it because it says the idea of the geodesic. Take the covariant derivative of the tangent, project it along the curve, okay, and you get 0. That means that the curve is as straight as it possibly can be in that space, and that's the geodesic. And then if I write this out in terms of the position of the particle and how it's moving as a function of tau, which is a parameter along the curve, then I get another expression, which is my geodesic equation, which we studied a great deal in our course on classical differential geometry. Okay, so some of these manipulations, I'm sure, are new to you. They're very elementary. But look back at our supplementary lecture 11, okay, which accompanies this video, and you'll see the algebra done there in a very straightforward fashion. So it should not be mysterious, and you should be able to master it completely. But now you see we get the punchline, a bit of physics philosophy here. We see that we started with Einstein's equation of motion. We didn't, okay, and that determines, given a source, what the gravitational field is. We'll solve it in various cases, see how that works. But that's the idea of it. But now I see, okay, on the basis of the fact that the Einstein tensor is conserved, that my energy momentum tensor satisfies the conservation law. And inside that conservation law is the fact that masses, it tells me how masses move. They move along geodesics, which are determined, okay, by what? By the gammas, by the gravitational field itself. So the equation of motion for matter follows from the equation of motion for the field, for the metric field, and that's great. Okay, I don't have to. See, we came into this thinking I have the equation of motion for matter, I have the field equation for gravity, and they're two separate entities. Okay, they play with one another, but here in fact they're joined at the hip. You tell me the field equation, and I'll tell you that the matter has to travel along geodesics. Okay, so matter creates a field. Okay, and then the field curves space-time, and that determines how matter moves. Okay, so and that's what we learned here. Okay, so it's more thoroughgoing than Maxwell's equations. It's deeper than Maxwell's equations, because Maxwell's equations don't give me the Lorentz force law; they give me the conservation of charge. Okay, and why did all this happen? Well, it happened because gravity is intrinsically nonlinear. Okay. This is my conservation law in gravity, and it includes the field of interest, the gravity field. Okay, remember the conservation of charge in Minkowski space doesn't refer to the electromagnetic field at all. So that's another contrast between the two theories, which is particularly interesting. And that's all I say in the next sheet. Okay. And then I say, okay, gravity is nonlinear. Why don't I find the Lorentz force law from Maxwell's equations? Well, because electrodynamics is not nonlinear. It's a linear theory. Okay. In the case of gravity, I have the universality of the force law. Okay, the idea that any bit of energy momentum attracts any other bit of energy momentum We saw that as a consequence of the equivalence principle. Okay, and and so that's playing a role in this idea. So that gravity attracts itself because gravity waves are going to carry energy. Okay, so the gravity waves that determine the geometry. Okay, determine how gravity waves move as well. Okay, that's what the field equation. That's what the field equation means, and that's different from electricity and magnetism, because electricity and magnetism, classically, the E fields and the B fields satisfy linear superposition. In other words, there's no natural mechanism for them to attract by the laws of electricity and magnetism, because they're neutral. Okay, the universality of in electromagnetism is that all charges attract or repel depending on plus or minuses. Okay, but E and B fields, okay, light doesn't carry a charge, and so the E and B fields, okay, just propagate through one another without feeling the presence of each other, and that's rather different than gravity. In gravity, if I take a gravity wave, okay, and pass it through another gravity wave, okay, there has to be interaction between them because both of those waves carry mass and momentum, and energy and momentum. Or, I must say that the interaction might be very difficult to measure because it will be tiny, 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 but it's there in principle. And in the case of Einstein's equations, in extreme environments like black holes, effects of that sort are important. Okay, and we'll find effects for the nonlinearity in Einstein's equations that will distinguish it from Newtonian gravity, and in ordinary circumstances, we'll find those effects. Right, the Einstein equations showed us that light bends when it passes near a large mass. Okay, it also will indicate that the orbits of the planets around the sun are slightly different than Newtonian predictions, and those are measurable effects, and of course they led to the substantiation of the theory. Okay. So we're interested in comparing the theory with experiment, and the one thing we want to do then is to see if it simplifies a great deal in the case where the gravity field is weak. Okay, I'm really excited about doing the opposite case and talking about black holes and rotating black holes and velocity dependent forces in gravity. But okay, we have to sober up. Okay, and make sure that we get Newtonian physics out as well, and then we can describe weakly interacting gravity waves propagating through space-time, which is to good approximation Minkowskian. So let's set down the formalism for that. So another theory topic is called linearized general relativity. I'm imagining I can find a coordinate system where my metric has only small deviations from my Minkowski metric eta. So h mu nu is much less than 1. That's got to be true in some coordinate systems. Okay, and I'm just going to go to first order. Okay, we're going to see that that's going to render the theory linear. Okay, all those nonlinearities that make general relativity so interesting and so self-consistent will be lost. So we'll have to look for some limitations of this approximation later. But it's typical of any kind of approximation you make. You go to a certain order, you stop, and so you've compromised certain nonlinear elements of the theory by doing that procedure. Okay, so it's not new, it's not special to this particular truncation process. We see that first order perturbation theory, when we do quantum mechanics, you compromise conservation of probability then, and perhaps you've seen that in your introductory quantum mechanics courses already, and you'll see it elsewhere, just an element of linearization of a nonlinear problem. Okay, so here's my weak gravity field. H is going to become a field which can propagate and have dynamics. Eta is my Minkowski space, just on diagonal 1 minus 1 minus 1 minus 1. Okay, so H, we're going to be able to view it as a weak field propagating in an otherwise flat Minkowski space. In addition, of course, it's also gravity. It's a weak source for space-time curvature. So I'll either use the language that H is just an ordinary field propagating in Minkowski space, and the rules of the game are special relativity, or then I'll also have the formalism to think of it as a source of space-time curvature. Okay. Okay. When we do a lot of our manipulations, we're only going to go to first order, and so there are a lot of simplifications that I can make. Okay, that I can make along the way. Okay, and we'll start looking at those next time. See, we're going to face some algebra. We're really going to get into the nuts and bolts of the construction of the field equation and simplify it and understand that H, the deviation from the Minkowski metric, satisfies a wave equation, and that'll be interesting and tell us a lot about gravity waves. And we'll start on that adventure tomorrow.